Welcome to This Dear Tailored. I'm Jessica Mao with the University of Texas at Austin. Today's video is first part of a 5-part series about factoring quadratic expressions. And today's topic is about how to make transition between factoring quadratic expressions and multiplying linear expressions. Before we get started, I want to draw attention to another video series we have about multiplying linear expressions. All of this work comes from an article that was written by Dr. Tricia Strickland in 2017, and she describes the way the students can use multiple representations to make sense of these algebraic concepts. First, we want to talk to you a little bit about the foundation for this research, which is the use of multiple representations. When we talk about multiple representations, we're talking really about the 3 primary kinds: concrete, pictorial, and abstract. You might also hear this referred to as concrete, representational, abstract, but both of these mean the same thing. In her article, Dr. Strickland includes the word integrated, which really reminds us that none of these representational types exist in a hierarchy. That is that concrete representations are not necessarily lower level, and abstract representations aren't necessarily higher level. We can expect students who know and feel comfortable using all 3 of these types of representations to choose whichever one makes the most sense to them, depending on the mathematical problems that you're solving. So let's get started, and first let's read the problem. The area of every room in the house is x squared plus 3x plus 2. What are the dimensions of each room? In this problem, we're trying to figure out what the factors are that we will use to multiply together to give us a product, which is x squared plus 3x plus 2. You'll see here that we're given some different rooms, some x values, and the areas of each room. And in her article, Dr. Strickland suggests that at this point, you can encourage students to attend to these areas by creating as many rectangular shapes as they can that equal to these areas. So let's get started. If we're going to create shapes that have the area of 30, we can draw a rectangle that have the dimensions of 1 and 30. We can draw another rectangle that have the dimensions of 2 and 15 that also equals 30 as a product. We can keep going and find the next one, which can be, excuse the squeakiness, 3 and 10. And finally, we can probably do one more of 5 and 6. So all 4 of these rectangles can have these different sets of dimensions that all have the product of 30. And we can have our students do the same for the next 2 products or 2 areas. So for 42, we can say that the first room has 1 and 42. The next one can be 2 and 21. Keep going. 42 is also divisible by 3, and that is 3 and 14. And finally, 42 is divisible by 6 and 7. So all 4 of these pairs of dimensions all have the product of 42. Finally, for 56, we're going to do the same thing. 1 and 56, 2 and 28. 3 is not divisible by 3, but it is divisible by 4. 4 and 14. And finally, draw. So my drawings are not up to scale. 7 and 8. So again, these 4 rectangles, rectangular shapes with their each dimension, they all multiply to 56. So once students have drawn all of the rectangular shapes or representations, you're now going to ask them to look at each set and attend to the relationships that exist between each of the sets of factors. For example, you can probably start with the set for 30 and ask them, what do you notice about the relationship between 1 and 30, 2 and 15, 3 and 10, and 5 and 6? And you're going to ask them to do the same thing for each of the sets of the rectangles and ask them if they notice any similarities across the 3 sets. After some exploration and some talking and some guessing, students are probably going to realize that at this point, this set right here have some similarity or some patterns going on, and that they can see the factors are different by 1 unit or by 1 number. So 5, 6, 6, 7, and 7 and 8. So then you can say that this is an interesting pattern. You're going to look at this data here and say, if these factors are related to the area of the rooms, how do they relate to this x value? So for example, you might say if the area is 30, how do the factors of 5 and 6 relate to the x value of 4? And how do the factors of 6 and 7 relate to the value of 5, and so on, 7, 8 for 6? At this point, students probably will realize that, for this set of factors, 5 and 6 is just 4 plus 1 and 4 plus 2. And the same as here, 6 and 7 is 5 plus 1, 5 plus 2. And likewise, for 7, 6 plus 1, for 8, 6 plus 2. And students can say, well, if that's the rule for this case, that looks like that for every x, the factors will be x plus 1 and x plus 2. And we can check this by using one of the set of the factors. We can say, if I were to use this, for example, if x is 4, sorry, it's so squeaky, 5 times 6, which is true here, and then we know that the product is going to be 30. So we know that these 2 factors, x plus 1 times x plus 2, are true for this problem. So now we can bring this back to our rule down here that for any x value, the area of the room will be x plus 1 and x plus 2 to get our product of x squared plus 3x plus 2. Thank you for watching this Dear Tailored. Make sure to stick around and check out our next video in the series in which I show you how to use manipulatives to factor quadratic expressions.